Chapter 9 is Transportation Assignment and Network Models. They are all transportation and assignment problems are also network models, so we can even call this chapter network models. So the problem, we will be discussing several problems. They all have this common feature, that is, they are all networks. So network would be like nodes represented by circles or connected by arcs represented by a line connecting one node to another node. So you'll have a bunch of nodes and bunch of arcs connecting the nodes, and then we have a problem with that as the backdrop. So these are the problems that we will be discussing. A straight transportation problem, and assignment problem is a variation of transportation problem. Then we have transshipment problem, maximum flow problem, shortest route, and minimal spanning tree. Okay, so these are the problems that we will be discussing in this chapter. Okay. So common terminologies, nodes, typically circles, and then the lines that connect the nodes are called arcs. We already talked about that. Okay, so first problem is transportation problem, where we have two types of nodes. One type of nodes is called sources, where we have products, goods that are available to be shipped. And the second set of nodes are called destinations, where we have demand, where these products should be shipped. So each of these sources have a limited supply of the product, and each of the destinations have certain amount of demand. Now from each source, product can be shipped to each of the destination nodes, and the costs differ. Okay, so you need to have costs for each of the possible transportations, and the problem is to come up with a transportation plan that minimizes the cost of transportation. And there are some variations that we can introduce into the model, like including production cost and things like that. So we are going to discuss this problem, Executive Furniture Corporation transportation problem. Okay, the first problem, okay, so here is the setup. So we have warehouses or maybe plants producing these products in 3 different locations, and there is a limited supply available. So we cannot ship more than that quantity out of Des Moines, or more than that quantity out of Evansville, and more than that quantity out of Fort Lauderdale. Now these are the demand points or destination points where we have a certain amount of demand which must be met. Okay. And each possible transportation has the cost of transporting 1 unit of the product. So it's $5 to transport 1 unit from here to here, and so on. Okay, so let's first enter all of this input data into the table. So we have the 3 supply nodes, then we have the 3 destination nodes, and these are the costs. So let's format this. Yeah. Then for each of the supply point, we have a limited amount of supply available. Okay, 100, 300, and 300. And then there is demand, 300, 200, and 200 over here. Okay, so let's complete the formatting here. Okay, the very first thing that you need to check is to make sure that there is a feasible solution for this problem. So which means, since we have to meet the demand, we must have sufficient supply. If you don't have sufficient supply, then you're not going to be able to find a solution. So let's check this out. So let me, okay, so total demand is sum of these three, 700, that's the demand, and we do have 700 in supply. So this is okay. So this is going to work out. All right, so our decision variable here is how much to ship in each possible arc. So how much to ship from Des Moines to Albuquerque, Des Moines to Boston, Des Moines to Cleveland. How much to ship from Evansville to each of the three cities, and same here. So we can set up 3, 3, and 3, 9 cells, each representing transportation from a given city to a given city. Okay, so this is going to be our changing cells. So how much gets shipped out of Des Moines is going to be the sum of these three cells. So we can say sum like that and copy that down. So that will be the total units shipped out of each of the three cities. Then if you sum column wise, that will give us the total quantity shipped into each of those cities. Okay. Now what is available is that for each supply city, and we cannot ship more than what is available. So the relationship here for the constraint is less than or equal to. All right. Now what is available, that the demand is given by that. Okay. Now here we can say what is received must be greater than or equal to demand, or just simply demand will work. So you need to start with an apostrophe for the equal to sign to be entered as a label. Okay. And so the total transportation cost is then some product of cost per unit and the number of units shipped. So there will be some product, cost per unit, and the units shipped. And that needs to be minimized. So let's color code that as an objective function, and we'll color code these as input. So now we have the model set up, and here we have to minimize the total transportation cost, and the changing cells are these, and the constraints are what gets shipped out of the supply points has to stay within what is available, and what gets shipped into the destination points must be equal to the demand. Okay. Non-negativity, simplex LP for solving method. Click solve, and the solution is found. Okay, I forgot to format this. And one thing we need to notice here, the transportation problem, because of the structure of the problem, you're guaranteed integer answers even without entering integer constraints. Okay, so just regular LP will always produce integer answers for you.